Okay, so my objective here in this lesson is going to be go through an example problem. It's going to be number 20 from page 66 of the Giancoli 6th edition, which is used for AP Physics B. The objective is going to be to go through the problem, an example problem, and show you how you should be structuring the problem to limit any mistakes and so that we can see what it is you need to be doing and how to set it up. So let's look at this problem and hopefully you'll see probably what I think is the best way to go through it and look at how to solve it. Romeo is chucking pebbles gently up to Juliet's window, and he wants the pebbles to hit the window with only a horizontal component of velocity. He is standing at the edge of a rose garden. Why that's relevant, I don't know. 4.5 meters below her window and 5.0 meters from the base of the wall. How fast are the pebbles going when they hit her window? So firstly, let's understand that there's some building and there's a window. Romeo, oh Romeo, he is, let's kind of put a dotted line from here. He is 5.0 meters. I'm assuming that he's not really throwing from ground level, he's throwing from, say, shoulder height. So at that shoulder height, he's 5 meters away horizontally, and then vertically 4.5 meters in the y component. So we have a y component, which is the vertical, and the x component. So let's keep that in mind. Now let's look at how we should be structuring this. The first thing that we should do is take a look at what equations we have to work with. Either that or looking at what information you have. Well, let's go ahead and look at the information that we have and then see what equations we might have that can fit those needs. We know that there's going to be an x component velocity. He only wants a horizontal component velocity, and we don't know what that is. So let's kind of express that. So x component, that's going to be a final velocity in the x component, and we don't know what that is. So let's kind of keep that in mind, that that's what we're looking for. We have a y component final velocity. If he only wants there to be a horizontal component, that means that the y component at that time will be equal to 0. So the final y component velocity will be equal to 0. That is meters per second. The y distance, and so I'll just use y to denote that, is going to be, as we said, the 4.5 meters. That's the final distance. And since the initial distance we're going to treat as 0, that means that I can just say that the change in the y position, or the displacement in the y direction, is 4.5 meters. And I can also do the same thing for the x component, that the change in the x component is going to be 5.0 meters. And those are both going to be positive. We generally will denote the up direction as being a positive direction, and, well, for the horizontal component, I can treat whatever direction I want to be positive. That makes it easy, and so that's what I'm doing. The change in time, I don't know that, but that's something I'm going to be looking for as well. So before I can even find this first initial thing of the velocity in the x component, the final velocity, I'm going to actually be looking for the change in time first. I also want you to keep something else in mind. I had noted that it's going to be the final velocity in the x direction, but please be aware that in the x direction, the velocity does not change. There's nothing affecting it. We are not going to take into account any sort of air resistance, and there is no gravity effect in the x direction. Gravity will only affect the y direction. Please keep that in mind at all times. So I'm going to go ahead and get rid of that little final annotation there because it's not needed. The initial velocity in the x direction will be the same as the final and the same all the way through. Okay. So now that we have written down things that we know or need to know, we can start writing down some equations. On page 38 in this book, we have some kinematic equations that we can look at and figure out, okay, well, what things can we find from this information? So let me just go ahead and start writing down some of those kinematic equations. Now, in the book on page 38, they have this as an x instead of a y, but I want to look at the y component first. Please, oh please, break these down into their components anytime possible and look at just one component at a time. And generally speaking, you want to look at the y component first before going into the x component. So we have y equals y naught plus v naught t, and again, this is going to be in the y direction. I'll put just a little annotation there. Plus 1/2 at squared. Again, that's the y direction. That's going to be gravity. Whenever you have the letter a, lowercase a, for acceleration, if it's gravity, it's going to be a negative value because, as I said, up is positive, down is negative. So when you drop something, it clearly wants to go down. So the 9.8 meters per second squared going in for a, that will be a negative value. In any equation that you see that has a lowercase g to denote gravity, you're going to put a positive value for that. So in this case, I'm going to put a negative value. Otherwise, if it was a g, let's just say, for example, if that was a g, then that would be negative. And that's the way the equations are set up sometimes. But I think for now, I just like to keep it this way. Just that way, it helps you understand that there is actually a direction to it. All right, so that's one equation that we can use, but that's not going to be the first one that I use, actually. Instead, I have v squared equals v naught squared plus 2a, and again, they have an x in the book on this page, but I can just change it to y, so it's y minus y naught. Well, I don't know why not. Sorry, bad joke. And what I prefer to do is, hey, that's the same thing as delta y, so I'm just going to replace it with that. Okay, so what I'm going to do is I want to find what my initial velocity is. If I look up here at things that I need and want to know, I have a final y direction velocity, but my initial y direction velocity, I don't know that. So that's something I'm going to be looking for right there. I suppose I should have really expressed that right off the bat, that hey, here's something that maybe I might want to know, but I don't yet. So that's one thing right there is I want to know the y direction initial velocity, or y naught. Okay, so I can use the same annotation all the way through. Put a little y there, and a little y there, and a little y there, just to keep showing that we're looking at just the y direction here. Okay, so let's express this and solve for Vy naught. So the final y squared minus 2a, keep my little y there, is equal to Vy naught squared, and then I can just take the square root of each side, and everybody always makes fun of my little square root symbol. You can do the same. I'm sure you're doing that at home at your computer. Haha. Okay. And so now I can solve, and I can certainly assume that you can plug this into a calculator properly, but what the heck, I'll just show you all the numbers. So the final velocity in the y direction is 0, so that's 0 squared, of course, and that's meters per second, minus 2 times a negative 9.8 meters per second squared, and the change in y is 4.5 meters. And that will give us a value, an initial y component velocity. Here I am at school on a Monday. It's actually Labor Day. Nobody's here except for me, and the bells are still running. Awesome. So we have 9.4 meters per second in the y direction initially. That's great. Makes me feel better about myself. Yay! Okay. So now that I have the initial y component velocity, I can figure out how long it's going to be in the air for. That, remember, that is just a completely vertical velocity. And so with that, I have an equation from page 38. One of the kinetic equations is v is equal to v naught plus at. And I want to solve for time. So v minus v naught over a is equal to t. And I'll just extend my page a bit more here. And here are my values. I have a final velocity in that y component direction of 0 minus my initial of 9.4 meters per second. That will give me a negative value, but remember that acceleration, when I'm plugging it in for an a, it is a negative 9.8 meters per second squared, and that's going to give me a time of 0.96 seconds. Keep in mind that it's not an exact value, that is rounded off, but no biggie. So a time of 0.96 seconds, and now that I have a time, we can do something very simple here. Keep in mind that the amount of time it takes for it to go up in the vertical, it's the same time that it's taking to go in the horizontal as well. So let's look at some things that I have. I have a change in x of 5.0 meters. I have a change in time of 0.96 seconds. And again, remember, we want to know the x component velocity. We don't know that, but look at these three things that we have, and two things that we have, and one thing that we need to know. Well, can't get much more simple than that. So 5.0 meters over the change in time in 0.96 seconds. And it gives us a velocity of 5.2 meters per second in the horizontal direction. The first equation I wrote down, if you notice, we didn't even use. Where are we? There we go. So this equation right here, I didn't even wind up using, and that's fine. Go ahead and just write things down, and you look. Here I have this equation, and if I were to look at what things I have and what things I need, it didn't suit my needs to where this next equation here that I'll underline in green, this one did suit my needs just fine in order to find the upwards component velocity, and then I was able to find the amount of time it took. Once I found the amount of time, I know the distance. Remember, velocity is not going to change in the x direction. So here's a recap of what I want you guys to keep track of. First off, whenever you see a problem, go ahead and just write down everything you know and the things that you think you might want to know or that could be useful to know. Sometimes they will give you information that you absolutely will just never need. For example, the rose garden. It's kind of a lame example, but sometimes you'll get some quantities of values that you just will not need. But go ahead and write those things down. You could tackle the problem more than one way. Some ways you could use that information, some ways you perhaps don't need it. So the first thing to do is all this stuff. That is generally going to be your first approach. Thank you very much. That's going to be your first approach. Go ahead and get those things done. So that way you can look at it, see what you have, see what you need, and then go ahead and start writing down your equations. The other tip is notice how I had started with, let's go ahead and underline, let's see, the one that I have underlined in green here. Please take note that I did not plug in numbers. I manipulated the equation a couple of steps before I did anything. I solved with the variables. I solved for the variable that I'm looking for. Please do that. It's as the equations become more complex, you will get yourself into a lot of trouble by plugging in the numbers too soon. It'll become very messy. You'll lose track of things. You'll have a hard time keeping track of units sometimes. And so my other strong suggestion, and the way that I really want to see things on a test and things like that, make sure that you manipulate the equation before you go plugging in any values. And I suppose that's it. And then the other thing is that I would personally like to see is when you do come up with the final answer, give it a little bit of a circle or box, and when you come up with some other important things, you can do the same thing there as well. Actually, I suppose I should go around my wanted variable as well. So for example, here I have x equals those things, and so if I'm really going to harp and say, hey, this is the way I want it, that is really what I'd love to see every time with your work structured out and all the steps shown. So hopefully that's helpful, and you guys have a good one.